All right, so let's start the class. So in yesterday's class, we had ended the class with different scheduling policies. We had studied about FCFS and then we went to prioritized scheduling. Okay, so there we have seen that if there are arrivals that are incoming at the output port, then those arrivals are basically classified as per their priority into different queues, that is high priority queue or a low priority queue, and then the server, which is basically the link layer module, which is going to um, put different information, header information on each of these packets. So that acts as a server, and then it will basically access the packets from the different queues depending upon the priority, and then there will be subsequent departures as and when the packets are basically served by the excuse me, served by the server. Okay, now what we had seen is that within different, between different queues, we have prioritized scheduling, but in the same queue, we have FCFS, a way of scheduling the packets. Okay, so this is how the packet arrivals were happening. So you have an arrival of a very high priority packet, and it will be definitely served because of its high priority, and it departs. Then we have number 2, which is a low priority packet, and then number 3, which is again a high priority packet. So this is the way the sequence of arrival happens here, and the sequence of service happens like high priority packets are served first, they get departed, and then we serve the low priority packets. Okay, so this is what happens subsequently as and when packets are arriving at the queue. Okay, so this is what we had done in the last class. Today we are going to do next scheduling policies. So we had studied about FCFS and priority scheduling. So today we are going to study about round robin scheduling policy. Okay, so round robin is pretty simple, as you all know. What will happen is at each of the queue, so basically it is like giving fair share to everybody, right, or fair access to everybody. So the server will basically check each of these queues one by one, and then it will try to take packets from each one of them turn by turn and then serve those packets. Okay, so all of these packets which are at the head of the queues, they have to wait for the turn whenever the whenever the server will come and um, take the packets. Excuse me, just give me a moment, please. Am I audible? No.
Yes, yes, ma'am. You are audible.
Okay. So, so what happens in round robin scheduling is whenever there is traffic that is arriving, that traffic is basically classified into different queues as per the class of application that it is going to serve, or the packet base as per the class of application the packet belongs to. So these are the different classes of applications, and the corresponding packets whichever arrive, they are sent to the corresponding queues. Okay, Now the server here basically will select each packet turn by turn for servicing, and there will be subsequent departures. Okay. So as it was done in the case of prioritized scheduling also, that any header field can be considered for classification of these packets into the different classes. All right. So this is what we have already discussed, that each packet will be taken up completely by the server one by one, and then it will be served by the server. So that was pretty simple. What we are going to do now is a different scheduling policy, and that is known as weighted fair queuing. Okay, it is actually a variant of round robin scheduling. Okay, so how does it work? So what we do is we give weights to each of the class. Now why it is being done? Okay, so you can say that round robin can be a fair kind of scheduling policy where every kind of customer or every class of customer is going to get the same treatment. Okay, but think from the perspective of the user. Okay, and even the ISP. So first think from the perspective of the ISP, where the ISP has to provide better performance for those customers who have actually paid a very good or large amount of money to them. Whereas there is other set of users which actually are looking forward to a very time sensitive application, or an application which is very bandwidth sensitive. Okay, so depending upon these issues, we cannot always give or always treat everybody in the same manner. So there has to be some kind of prioritizing in that case. Okay, so you can ask me that, ma'am, we can do always prioritized scheduling. Why are we then going to the weighted fair queuing? Because prioritized scheduling is not always fair. Okay, so by using weighted fair queuing, we are trying to have a fairness also in this. Okay, now how it is happening here? So we put some weights on each of the classes. Okay, now then we normalize this weight, as you can see here. Okay, so each class I has weight Wi and gets weighted amount of service in each cycle. Okay, that is given by this normalized weight. Okay, now for each one of them, for each one of the class, you have a minimum bandwidth guarantee. Now depending upon this value and what is the available bandwidth at the server, okay, this link capacity, what is the capacity that it can provide and what is the normalized weight, depending upon these two factors, the service of each one of these classes is done by the server. Okay, there is a full detailed algorithm for this. This is fully there in the advanced course, but because this is a very primitive course right now, so only this much information is fine for now, that you have weights in each class corresponding to each class. You get the normalized weight, and in each cycle, depending upon the available link capacity and the normalized weight that you are having, the service is done by the server to each of these classes. Okay, so why it is done? Because as I already told you that for different kinds of applications that a user asks for, they might ask for certain features. So minimum bandwidth guarantee is one of the properties that a user can ask for. Okay, so if you classify these queues as different classes of packets or classes of traffic that is arriving, packet traffic that is arriving, so these classes can have different bandwidth guarantees, and with these different bandwidth guarantees, the weight will change. Okay. So by now, what we have studied is that what happens in the inside of a router in terms of what's at the input port, what's in the switch plane or switch fabric, and then what's at the output port. What are the different scheduling policies, or basically how the arrival of packets is managed at the output port, at the input port, and also what are the different types of switch fabrics. So that's what we have done until now. Today we are going to start something different, and that is the Internet Protocol or IP. Okay, so it's very important. This will be helpful throughout your life. Okay, so please pay attention to this one. Okay, so Internet Protocol, there are two main concepts that we are going to study here. One is datagram format and another is addressing. Third and fourth would be network address translation and IPv6. Now, before we go forward, let's first see where are we currently and what are the different modules that we are going to study. Okay, let's see what are the different network layer functions. So we know that most importantly, network layer functions are the different routing algorithms. So these are the different path selection algorithms. So this module is basically working for that. So you have these path selection algorithms are implemented in the form of routing protocols. We will read about the routing protocols in this same chapter only. OSPF and BGP are some of the known routing protocols, and we can also study about SDN controller. All right. Now, result from this routing algorithm is used in the forwarding table. Okay, to get what is the exact address, or sorry, what is the exact output port to which the particular packet needs to be forwarded. Okay, what's next? The other one or the other set of function is the IP protocol. Okay, what does it handle? It handles that, see, you have received a segment from the transport layer. Okay, you have to now make it as a datagram, so therefore you need the datagram format. Here, what is the network layer's task? You know that it has to give an address, right? It is basically uh, concerned, the network layer functions are basically concerned with the host to host communication, right? So that means you need the addressing of the host, and you need to put those addresses in the particular datagram also in that format. And how this packet will be handled, that also, those conventions also are under this IP protocol. And the fourth one is ICMP protocol, which basically deals with error reporting and router signaling. Okay, signaling for certain important messages. So that we will read later on when we are working with ICMP. Okay, so as of now, what we have studied is we have just seen that what is happening in the forwarding table in the terms of longest prefix matching, and we have just seen that how the router actually works out. We have not seen anything about routing. We have not seen anything about any of these two set of functions. Sorry. Okay. So eventually, when we are working towards the end of this chapter, we will know all of these modules thoroughly, hopefully. Okay. So let's go ahead. So this is the datagram format. Okay. So it is of so this datagram format, we have the 32-bit format here where we have different variable fields. Okay. So we have the version of IP. All right. All of you may be knowing by now that we have IPv4 as well as IPv6. The header length, the type of service that it's being asked or it is asking for, then the length. We have a 16-bit identifier. We will see what it is about. We have different flags. We have fragment offset, the time to live field. Okay, So this is a very important field, the time to live field, which basically talks about, it essentially means that what is the lifetime of this packet, okay, or this particular datagram here in this case. So time to live field will determine that after how many hops, or basically after how long your packet has to be discarded. Despite whether it has reached the destination or not, it really does not matter. The time to live field is finished. In that case, the packet should be discarded. Okay, so there's a very important factor or a very important field here. The upper layer protocols or information, the header checksum. Then you have the source IP address and the destination IP address. The most important things. Any packet, if you have to send, you have to have the source and destination IP address. There's an options field that is required if you want some. We will see why this options field is kept when we when we study these in detail, and then here you put the payload. Okay, in the last one. All right. So I've already told this, but yeah, I should have done this one. Anyways, so this length is for the total datagram length. Okay, it can be at the max of 64,000 bytes, and typically it can be 1500 bytes or less. All right. So we have different services. Okay. So this is the time to live field, as I told you, that it determines what is the maximum number of hops or maximum amount of time that your packet can actually live for. So when we are talking in terms of the when you are talking in terms of networking, we generally consider this in terms of hops. Now, what is a hop? Okay, so when you look at your any network that is given to you, let us assume that you have a connection between two devices and there's a router in between. Okay, so that the one distance that you are your packet is basically moving from one host to another host without going through any other device in between. Okay, so basically there is one device, and let us assume that it's a wired connection, one device, a wired connection, and another device. Okay, so this movement of a packet from device A to device B without having any other device in between. So straightforward, there's a medium and it is moving from one device to another device. That will be called as a hop. Okay. Now, as I was giving an example, if there are two devices A and B and there's a router in between, so if your packet has to move from A to B, then it will require two hops because it will move from A to the router, that is one hop, and then the router to B, that is hop number two. Okay, so like this, if you can imagine, there are so many routers in between, or there can be so many routers in between for very long distance communications over the internet, right? And there is too much of it's basically a network of different devices or different core devices which are there. Okay, so the time to live field essentially determines that how many devices you are moving forward to reach your destination. Okay, so so if the TTL field is suppose 8, so at every hop that counter will be decremented. Once it reaches 0, even if you don't reach the destination, the packet will be dropped. Okay, so this is what the time to live field means. Okay, this I've already told. All right. Now, this 16-bit identifier, the flags and the fragment offset. Okay, so I was telling you about these things, but I told you that the 16-bit identifier we will read later on. These three fields are basically concerned with fragmentation and reassembly. Okay, so fragmentation and reassembly, we will see that how it is important here, and what does it actually mean. So you're basically either breaking the entire data into small fragments, and then at the receiver side you are trying to reassemble them, right? So that is the breaking part is fragmentation, and then assembling it correctly, that is reassembly. Okay, so for that we need some information that is given by these three fields, that is a 16-bit identifier, flags field, and the fragment offset. So in the same chapter we will see how we can do this. All right, we know that header checksum will be there. Then we have a 32-bit source IP address and 32-bit destination IP address. Okay, now what are the options, please? Options can be there. For example, what's the timestamp you're putting on the packet, if you want a timestamp on that. And you can also record the route that has been taken by the packet to reach the particular destination. Okay, so these are some option fields that can be used as and when it's required by the administrator for the given kind of application. Now, given all of this information that this datagram basically has, okay, so we have 20 bytes of TCP, 20 bytes of IP overhead. Okay, so 20 bytes of TCP overhead, 20 bytes of IP overhead, and we also have some application layer overhead for TCP plus IP overhead. Okay, so total overhead for all of this is 40 bytes plus application layer overhead for TCP plus IP. Alright. Okay, so we are going to start with IP addressing. So what is an IP address? Okay, these values, which is given in this diagram, 223.1.1, 1.2, 1.3, etc. You all are aware of these values. Okay, you have seen them thousands of times. So what are these? We all know that these are known as IP addresses. Okay, what we are going to study in this chapter is that what do they signify, how do they come from, or where do they come from, and if I have a device, then how do I get this IP address, or from where do I get this IP address, and what does it actually mean? Okay, so a lot of information is associated with just these 32 bits. Okay, so we will see all of this in this chapter. So you see all of these things as decimals, right? 223.1.1.1. Okay, but essentially your datagram or your system is looking at this as a 32-bit identifier. Okay, so each host is actually associated with a, or actually represented as a 32-bit identifier. Okay, now there is this term which is known as interface, as you can see. So what is an interface? Okay, so interface, this term, if you have seen it or heard it anywhere, you will see that we generally say that router interface. Okay, so what is this interface? So interface is nothing but it is a connection between the host or router and a physical link. Okay, so you can see here, okay, there's a router and it has three different connections associated to it. These three different connections are basically These different connections are basically connected to three different hosts again. Okay, so interface is nothing but the connection or the way of connecting to the physical link. So if you have a device, how you are getting connected to the physical link or the medium through which you are actually transferring the data, that is known as your interface. Okay, so a router also has multiple interfaces. Okay, and what about the devices that you have in general? Okay, You have your mobile phones, you have your Wi-Fi routers at home. Okay, so in general, we our devices also have one or two interfaces, right? If you have your router at home, you can use either an Ethernet connection or you can use a Wi-Fi, right? Whereas in case of your mobile phone, you can connect via either cellular access or you can connect via Wi-Fi by essentially connecting it to the Wi-Fi. Now, what we see here is this decimal notation, that is 223.1.1. That's how we as users represent an IP address. Okay, but what is essentially inside it, or what is how it is depicted in terms of by the system, that is in terms of these 32-bit IP addresses. Okay, so here you can see that the first part, it basically represents this 223, then 1, then 1, and then 1. Okay, so this representation of these 32-bit address into the decimal notation is known as dotted decimal notation or dotted decimal IP address notation. Okay, this is in general done so that it becomes easier for the user to uh, you know uh, classify these addresses or classify a host in terms of the IP address that is given to it. Okay, all right. Now let's go further. So we have talked about interfaces until now. What we are going to talk about now is how are these interfaces actually connected. Okay, so these connections we will see when we are looking at the next layers. Okay, so let's go further. You can either connect, as I already told you, that you can either connect via your Ethernet cables or you can connect via Wi-Fi access. What we are going to study now is subnets. Okay, I don't know how many of you have heard about this term subnets, but if you go to your systems network administrator, or in the sense that in your network settings, if you go in your system, you will find out this term subnet. Okay, so what is this subnet? What does it actually mean? So subnet essentially determines that what are the devices or what are the interfaces that can reach each other physically without passing through another router. Okay, so look at this diagram here. Okay, there's one router here. There are three different connections. These three different interfaces here. These interfaces are connected to several hosts. Okay. Now look at the host with IP address 223.1.1.1 and 223.1.1.2. If you have to reach from 1.1 to 1.2, then you can simply say that these belong to the same subnet, because you do not have to pass through this router to get to this particular host. Okay, and this is not the packet service that I am talking about. Physically, you do not have to pass through any router to reach this particular host. So essentially, all the hosts which are basically connected to a given interface without the intervention of a router in between, that those will fall under the category of a subnet. Okay, so why do we need a subnet? Okay, so see, we have a 32-bit IP address for every host. All right, if you are, so we need this for address or identification. Now, if you see your postal address also, your postal address also has different classifications. The first is your house number, then comes your street address, then comes your colony. and then after that your city, and then what is the pin code of your city. So similarly, when we are talking about IP addresses also, we are basically classifying uh, the address in such a way so that it becomes easier to actually find out the host. Okay, so subnet is basically, or subnet part of the IP address. That part of the IP address basically helps to determine that what is the main cluster that you have to look for if you want to find out what exactly or which exactly is the host of or which exactly is the destination host, right? So IP addresses have two parts. One is the subnet part and another is the host part. So subnet part will basically determine that which subnet your device belongs to. Okay. So the subnet part is essentially the higher order bits of the IP address, and rest of the lower order bits basically determine that what exactly is your host part, that is which is your host. So essentially subnet is like your colony and host part is like your house number in your colony. Okay. Now how do I define a subnet? Okay, so this is a very naive answer that has been given here. It's like, just imagine that if you just remove or detach an interface from a router and create like separate islands of simply hosts together, those hosts will actually form a subnet. Okay? So if you think logically, it's nothing but all the sets of hosts which can be reached from each other without the intervention of a router. Okay, all of them are becoming a subnet. Okay, so let's see. Here in this figure, you have different hosts with their corresponding IP addresses and the router with different interfaces and corresponding IP addresses for them too. Now the subnet part will become all those interfaces which can be reached from each other without having a router in between them. So these are the ones which will form a subnet. Here, all of these will form a particular subnet, these IP addresses. Okay, because they can be any packet that is arriving at this any of these devices, so they can reach each other in this particular collection or in this particular classification without going through a particular router. So these will form a subnet. All right. Now, how do we represent the subnet part? I just told that subnet part is basically the higher order bits of the IP address. But how do I determine in this dotted decimal notation that, oh, which part is the subnet part? Okay, so this is represented in terms of this subnet mask, which is known as /24. I mean, in this example, it is given as /24. It can be any other number too here. And in this example, we have considered a 24-bit subnet mask. So this, as an example, we have given 223.1.3.0/24, which means in this IP address, that is 223.1.3.0, the higher order 24 bits are representing the subnet part of the IP address. Okay, the rest of the parts, that is rest of the 8 bits, those will represent the host, exact host. So similar with all the other subnets. Now, so in this diagram, we have 3 subnets altogether, as we just saw. Okay. Now, can you tell in this diagram, in the given diagram that we can see here, how many subnets are there? Can anybody tell how many subnets are there in this diagram?
Ma'am, is it 3?
Uh, how are you saying 3? Because all the other ones which are connected to the hosts, right?
Yeah.
Yeah. Okay, 3 is not exactly correct, but yes, there are 3 subnets. But any other answer apart from 3? 3 is not exactly a correct answer. 3 is just a subset of the correct answer. Okay. So what's the correct answer? So what are the total number of subnets here? Remember that the definition of subnet is that you can reach from one host to another or one interface to another without moving through another router. Okay. So can anybody give an answer to this question? How many subnets are there?
Can the network of the central routers be considered the subnet? Like, because they have interfaces of their own and they are all connected to each other?
Yes, as per the definition, that is true. Isn't it? They are also hosts only, right? They can be the core network hosts, but still they are systems and systems. They are basically having interfaces, and these interfaces are connected to each other. So if there is no router in between and they are basically connected, so then that becomes a subnet, isn't it?
Yes, ma'am.
Okay, so how many subnets are happening?
4.
4. How come?
The three
Can you become a single
islands.
sub?
Ma'am, it
3
will be
islands, but then
Sorry.
3 islands. You said 3 islands make 3 subnets.
And the
Okay,
central one.
central one is one subnet. You are saying.
Yes, ma'am.
Again, let me
Because
tell you the definition. Let me go back to the definition. Okay, what's the definition of a subnet? Device interfaces that can physically reach each other without passing through an intervening router. Okay, a router is also a device. So, device interfaces that can physically reach each other without passing through an intervening router. What is an interface? Interface is basically allowing your device, the way to allow your device to physically attach or physically communicate with the transmission medium, right? It can be either Ethernet or it can be a wireless medium. So go to the figure. So for each of the routers, we have 3 interfaces, right? In this diagram also. So how many subnets will be there?
a total of 6.
Yes, there will be a total of 6 subnets. Okay.
um, ma'am, but each router is connected to the two other routers directly without any interface.
No, no, no,
Like
no, no.
without any router in the middle, they are all connected to each other, forming a triangle, right?
Yeah, so that is, they are routers, no? If you want to go from one router to another router, okay?
Yeah, I can go directly now without passing through any router if I want to go from one router to the other.
Huh. Let me name these routers. Okay, so these are suppose this 9.1, 9. No, no, not like this. The top one, let me call it as A, the bottom one, left and right being B and C. Okay. If you want to go from A to B, you can go directly from A to B. Okay. If you want to go from A to C, you can go directly from A to C. But if there is the path is not there between A to C directly, you have to go via B and then to C, right? So there is in between your B comes. Okay, so A to B is one path, B to C is one path, and C to A becomes another path. There's no direct path from A, B, C connecting them together. Okay, so that is why they will become not a single subnet. They are basically forming different subnets altogether. Is this clear or should I repeat once more?
So there shouldn't exist any additional path except the direct path for a subnet.
subnet is basically, it's like, you can just draw a straight line between the two devices. Like you can simply just put the devices all together. There should not be any other router in between. Okay, that will create a subnet. So there are two interfaces in let's look at this. Okay, let's look at this A and this guy. I hope that my mouse is visible to you people. If not, then let me know. Let's look at this 223.1.7.0 and 223.1.7.1. These are two different interfaces belonging to two different routers. Okay, so these interfaces are allowing this particular router to connect to the medium. That is why they have this address associated to them. Now, if there is a packet that needs to move from this interface 223.1.7.0 to 223.1.7.1, in between it does not face, the packet does not face any other router. Okay, so that is why these two IP addresses will fall under one subnet or one category. Okay, then again the rest of the other routers also, if you think of, sorry, other interfaces also, if you think of, when they do not have any other router in between, in that case they will fall under one subnet. So basically what's happening is that think from a point of view of the colony and your house number kind of example that I gave you. Okay, so there are many ways in which certain colonies are defined, like you know some same type of people are living in the colony, or let's like Bengali colony or army colony, like that, things like that happen, right? So the outlier part is minimum. Whenever there is not an outlier, we just form a set of people and then call them as a colony, right? Similarly, in these cases also, what's happening in the case of subnet, like all the interfaces which are connected together without the intervention of any other router, they will form a subnet. So in this case, that is why you are having 6 subnets. Okay, like this. In each subnet, you will have your hosts which have different IP addresses, but this subnet part will essentially determine that what is the colony they belong to, right? So if you see the first subnet, that is the top one, you will see that the IP address is like 223.1.1.1, 1.1.2, 3 and 4. These are the 4 devices. Now when the subnet changes, the IP address also changes a bit. So how does it change? 223 dot, so if you see the next subnet here, it's 223.1.9.2 and 9.1. These are the same interfaces, same subnet interfaces in the same subnet. So they are numbered like this. Similarly for all the other subnets which are present in this figure. Okay. Now here it is given as what the question is there, that what are the /24 subnet addresses. So this you will understand much better if we study a little more on the IP addresses that I will also teach in the next class. Okay, what is the way in which IP address classification is done? We have already seen that 32 bits are 32-bit IP address is what we are looking at currently, that is IPv4 addressing. Now, if we do a /24 addressing, you will see that if you consider the variation after the 24 bits for hosts, so if you just consider the first 24 bits, you will see that that is why all of these hosts are given as 223.1. And then after that, there is any change, whatever is there. Okay, so you will see that which ones are the 24-bit addresses. So these are the ones which are /24-bit subnets. Okay, so there should be a little more understanding of these. So I will not ask this question right now. We will again move forward a little bit more into IP addresses, and then we can probably ask this question later. All right. So one way of trying to find out that what is the IP address of a host, and according to that IP address of a host, how do we identify which host the packet needs to go? Okay, so what we have seen, one way is that you find out which subnet it is, and then after that you will find out what is the host depending upon what is the rest of the or the last lower order bits. Okay, now this representation of the subnet part and then the host part of a given IP address, that falls under a classification which is known as CIDR or CIDR or classless interdomain routing. Okay, it is pronounced as CIDR. Okay, so what we have in CIDR, as we have already seen, that we have an arbitrary length subnet part which will define that what exactly is the set of hosts which are basically connected without an intervening router, and then in that subnet part, what is the sorry, after the subnet part, the rest of the bits will determine that what is the exact host in that subnet. Okay, so we have seen that the address format is basically given as a.b.c.d/x, x defining the subnet portion of the address. Okay, so this is given here in this chapter. So in Kuros and Ross book, if you go and see, they have only put up to CIDR. Okay, they have not put anything else on how the classification of IP addressing is exactly done. That means this is how it is done nowadays using CIDR. So that is why they have given CIDR like this. But earlier it was not used. I mean, CIDR was not used. So IP addressing is basically done in two ways. One is classful addressing and another is classless addressing. This falls under that classless addressing concept. The classful addressing again is a different concept altogether. So this, I will take one class for teaching the IP addressing, then classful addressing, and then all other some more concepts on that. Okay, so this is it, and yeah, this is what we have already studied. So here we have a 23-bit subnet, and then we have a corresponding host part. Okay. Now, the question that has been posed here is that how do we get an IP address? Okay. Now, this question itself asks two more questions, which is how does a host get IP address within its network? Okay, that means how do we get that host part of the address? Okay, we are saying that we have a subnet part and then we have a host part. Okay, so the IP address. So if I just put device in any subnet, I can get the subnet part, right? But what is the host part? So that has to be received. So how does a host get IP address within its network? And the second question is, how does a network get an IP address for itself? Okay, so that these are the two questions that need to be answered, and eventually when we read further in this course, we will find out that how to answer these questions. Okay. Okay, so first question, that is how does a host get IP address within its network? Okay, that is answered by DHCP. Okay, now there are two options which are given here. One is hard coded by sysadmin in config file. Okay, so this is like a very basic one which can be done just to teach somebody, but in real life when you are actually using the system and using the system for many other tasks, using the systems in many different interfaces in the area, so in that case you will require a different way of putting or adding IP address or getting an IP address for a particular host. Okay, also it's if you have millions and millions of devices, right? So If you hard code IP address for everybody, the options that you have is just a 32-bit address. Okay, so 2 power 32 is the only different options that you will get. And given the amount of population that we have in the world and the amount of electronic devices that are being used, that will be essentially finished out. Okay, if you hard code each and every device with an IP address. All right. So what we use is DHCP, that is Dynamic Host Configuration Protocol. This is a protocol which dynamically gives address to gives IP address to a particular host in a network. Okay, and it follows this rule, which is known as plug and play. Okay, so you know what it essentially means, that whenever you are um, adding your device to the network, only then you get the IP address. Okay, and after that, once you take out your device from the network, then that IP address is no longer valid for your system. Okay, so as and when you add your device into the network for use, then you get a dynamic IP address. Okay, this is the basic concept that is followed in case of DHCP, or dynamic host configuration protocol. I'm very sure that if you go into your um, system or settings for network, your network settings, you will find out what's DHCP and what are the corresponding values that are given there. Okay, so I will start the next class with DHCP. Today I will not start it. All right, so class is done as of now, but I do have an announcement. So see, after I told yesterday that